We have already been discussing carbon 13 NMR since last 2 classes. I discussed varieties of things about carbon 13 NMR. Especially I said we are going to record the carbon 13 NMR in a decoupled manner. That means we break all the couplings of carbons with all other protons. Then the spectrum what you are going to get correspond to single peak for each chemically inequivalent carbon. And what are the types of decoupling? We can have types of decoupling like completely broadband decoupled with NOE, without NOE, coupled with NOE, decoupled, all combinations we discussed. And I said basically what you do is you have to do the decoupling with NOE. That is the conventional carbon 13 NMR spectra recorded always. When we record such type of spectra, I showed that all carbons will not be of equal intensity. It could be because of symmetry. Symmetry will also give rise to different intensity, that is understandable. There is a symmetry, 2 carbons are overlapped, that will have double intensity, fine. But the remaining carbons which are attached to single protons or not attached to any proton should have identical intensities. But it normally not happens. This is because not only symmetry, the relaxation plays a dominant role. Especially the protonated carbons relaxes very fast. Non-protonated carbons like quaternary carbons, ipso carbons which are present in the molecule, they relax very slowly. Carbons attached to proton enhances and ensure that these carbons relaxes faster. As a consequence, they will have signal intensity more than other carbons. I showed that to record the carbon spectrum with identical intensities, what you have to do is you have to record the spectrum with relaxation delay or delay between the subsequent pulses which you apply should be 5 times that of the longest T1 of the carbon of your molecule. If a molecule has different carbons with different T1, find out the carbon which has the highest T1, longest T1. Take that value 5 times that one as the relaxation delay, then you will get all the carbons are of equal intensity. That is what I said. And continuing further from that today, this is an example of the spectrum where I showed you this ipso carbon is weak in intensity, whereas these 2 carbons double the intensity, whereas this para carbon is 1 intensity. In principle, these 2 will be of the same intensity, but because 2 carbons of symmetry is there, they are overlapped, it appears double the intensity. Only problem is this ipso carbon, this one, which is intensity very small, because as I told you, the non-protonated carbons relax very slowly. As a consequence, by the time you apply the next pulse, signal would magnetization of that particular carbon would not have relaxed back, achieved thermal equilibrium, would not have come back to Z axis. As a consequence, their intensities are weaker. Okay. So, how do you analyze the carbon 13 spectrum? It is fairly simple. You do not need to break your head. All you have to do is apply your knowledge, like how you use your knowledge to analyze the proton spectrum, same manner. As I told you, the chemical shift, the parameters which affect the proton chemical shifts, all those things will affect the carbon 13 chemical shifts also in the same manner. So, very easily you can start assigning. Take an example of the molecule like this. Look at the CH3 proton. We all know CH3 comes at a very high field. Okay, this could be CH3, and of course there is another CH3 here. This CH3 and of course this CH3 has a different chemical environment. If you look at the table where I showed where different chemical functional groups resonate in carbon 13 spectrum, you can find out CH3 which attached to the CH will be always around this range only, and I would slightly it is de-shielded compared to this one. So, I would say this is carbon 8 and this is carbon 1, then remaining is simple. We have 3 more CH2s, 3 more CH2s are. Which carbon is which is another thing which you need to understand. That is a different question. There is a way to do that. We will discuss that when we go further in the inadequate experiment. And of course, you come to the solvent. This is a solvent which is used. One solvent peak is here. In addition to this 3 is this thing. And if you come here, there are 3 quaternary carbons here, I think. CO, no, that's C4, C2 and C3. C4, C2 is this one, and C3. Okay, these are all CHS. C2 and C3 are CHS, and C4 is quaternary. Quaternary is very weak in intensity. because it relaxes slowly. Whereas C2 and C3 you see should have been attached to single proton, should have been of equal intensity, but somehow the C2 has a very long relaxation compared to C3. It is relaxing slowly. But basically you can assign more or less a sort of each individual peak to a particular carbon, and when there is difficulty with too many CH2s are present, which carbon is which CH2 carbon correspond to which peak, that is at more of detail. We will do that when we go further. Take an example of another molecule. It is a carbon 13 proton decoupled of this simple molecule. Here it is fairly easy for you to understand. Obviously we have 2 carbons which are CH3s here, and OCH3 is here, that comes to the downfield, that we know. So C1 is here, OCH3 is downfield, this is CH3, of course this is also C double bond O attached, but this is directly O attached. So this is C1, this is C4. Then there are 2 CH3s, 2 CH2s, 3 and 4. But if you carefully see, this C4 carbon is coming to the very high field, and especially the C9 carbon which is OCH3 is coming here. This is not CH3, this is CH2. And C double bond O carbon, this carbon and this carbon, they are not attached to proton, they are very weak in intensity. This is solvent. Solvent are always quaternary, they are not attached to any proton usually. So as a consequence the solvent peaks are generally weak in intensity, unlike proton spectrum where solvent peaks are huge. But here in carbon 13 spectrum solvent peaks are very low in intensity. Of course these two are protonated C6, C7, double the intensity, because there are equivalences that this is equal to this is equal to this. Because of the chemical equivalence you can clearly identify these 2 carbon signals are double the intensity for 2 carbons which are overlapped or which are having symmetry. So this is how it is, you can easily interpret this one. Go further, another simple molecule. Here it is easy to do that. Where do you get there are 2 CH3s, one is CH3 attached to CH2, another is OCH3, OCH3 comes downfield, it is here. Then we have a CH2 that has to be here, and then there are 4 aromatic carbons, 2 aromatic carbons here, this carbon is equivalent, this and this are equivalent. So we have 2 carbons of equal intensity, and then remaining C3, C7, C6 carbon, this one and this one, they are all quaternary carbons, very weak in intensity. Okay, so very easily you can identify and do the analysis, and interpretation is easy. But then here I made some rough estimate of these chemical shifts. What is the guarantee? What is this thing that what I have done is correct? My analysis is correct. How do we know my assignment is correct? Especially when you have phenyl groups. These are all okay. CH3, OCH3 we will not just generally get confused. Whereas in the proton here, which is C4, which is C5, I do not know. But there is a way to predict the carbon 13 chemical shifts. This is what is called the effect of the substituent on aromatic carbon chemical shifts. Depending upon what is the type of substitution you have, different proton chemical shifts, especially for aromatic carbons, we can easily predict. Very simple rule, like we can do for the protons, we can also do for the carbon 13. Take for example, this is a table where we have NO2 here, and NO2 if it is remember when I was telling you, I was trying to predict some of the couplings, some of the chemical shifts in the substituted benzenes in the proton spectrum. Identically here also, if you have different substitutions, you can find out the values or the contribution of each of these functional groups, substituent groups at different positions in the phenyl group. For example, I have a NO2 in a molecule in phenyl group. One of the this thing substituent is NO2. Then for the ipso carbon, this is the contribution. For ortho carbon, this is minus 4.9. For meta, this is 1.1. For para, it is 6.3. That means you have to find out the contributions for each of them, and then just do the co-addition of these things. You will get this value. I hope you still remember the phenyl protons also. In the example of analysis of proton spectra, I took 2 or 3 examples and I showed you based on the substitution of NO2. Simply first I took the example of the dinitrobenzene, where each nitro group has each proton has one ortho and one meta nitro, and I added that value and showed you basic value for proton chemical structure of the benzene. You have to take 7.28 and then add the substituent value to arrive at the approximate values of the predicted chemical shift for protons of the phenyl ring. Identically, you can do the same thing for carbon 13. All substituents are there, their values are given at for different positions. All you have to do is you have to simply take the value and add it up. And here the base value is taken again for benzene. Their proton chemical shift of 7.28, here carbon 13 chemical shift of 128.4 is the base chemical shift of carbon 13 of benzene. And then different substituents values will be taken and co-added. That is what you have to do. Take for example this methoxybenzene, OCH3 is there. Here there are 4 different carbons. There is a symmetry here, and these are same, this and these are same. I can calculate or predict approximate chemical shifts for each of these carbons. Let us start with carbon 1. Carbon 1 has OCH3 group in the ortho position. Go back to your table. What is OCH3 here? OCH3, if you see somewhere, OCH3 is here. OCH3, if the carbon is in the ortho position, its value is minus 14.4. If it is a meta position, 1.1, and para position minus 7.6, and if ipso it is 31.3. These values will remember, we will take this value and use it here. For carbon 1, OCH3 is in ortho position. I showed this value is minus 14.4 here. I have to add for that and I get this value. For 2, it is in the meta position. When I showed in the meta position is 1.1, please add it up, it is 129.4. This similarly for this one, the substitution in the para position, in fact instead of adding it is again subtracting, it is 120. For carbon which is ipso directly attached, and this is the contribution and this is the total chemical shift. So approximately like we did for the proton chemical shifts in the phenyl groups depending on the substituents, here also depending upon the position of the substituents, different carbon chemical shifts can also be calculated, and this is what it is. And these are the values we have obtained: 114, 129, 120, 159. See here 114, 120, 129, 158. All the experimental values are approximately equal. For look at the last one, 159.51, here 159.7. So close by. Of course, predicted values is predicted, not experimental. Authentic value is experimental. But to make the assignment easier, this is one way you can calculate. You can predict the carbon 13 chemical shifts, and that is how all these things can be assigned very easily. We go to acetaminophen, para-acetaminophen. This is what we also try to analyze in the proton spectrum, I think. Look at this one. This group, NHCOCH3 group, this substitution, you have to see its value for ipso, ortho, meta, and of course we also have a OH para. And you have to consider 2 parameters. Let us consider this proton 1. Proton 1 for ipso is OH and para is NCH3, and those values taken from the table. Ipso is 26.7 and para is minus 4.1 for this group and this group. Go back here and see the table. For OH for example, ipso is 26.7 and para is minus 7.3. So like this you can start putting NHCOCl3 is also here. NHCOCl3 ipso is 9.5, 9.8, para is 0.4. I have added this value here, ipso, and in the other case for this one, for the case of this OH, this carbon, ipso is OH and para is this one. So ipso OH value is this, para value is this one. For carbon 2, this is ortho, this is meta, values are taken. Carbon 3 again, this is a meta but this is ortho. Carbon 4 is very interesting. IPSO is this one, this value is minus 9.8 for IPSO, whereas for para is minus 7.3, and this is the value you are going to get. You can calculate the carbon 13 chemical shifts with additive factor like this, and this is what it is. Look at this for a carbon, for example 1, 2, 3, 4, 4, all the 4 carbon. I am not worried about this and this because we are calculating only for the phenyl carbons. Only 1, 2, 3, 4 if you see, this is 153. Go back to our calculation. This is C1 is 151. We are getting 153. For example, C2 is 115 and we are getting 150. Very precisely, if not precisely, at least close by to the experimental value you can calculate. And this is what the idea you have to use for making the assignment. In the previous examples when I took the assignment, I made a rough estimate based on the intensity and everything. But with that idea, use this table, calculate the substituent effect, and then you can make the assignment very easily. So, you can go back with the this thing, we analyze the spectrum of proton. If you remember, we calculate the proton chemical shifts based on its position, and same thing he can do for all the 6 carbons here. There are 6 carbons. For this carbon 1, IPSO is NO2 and meta is COCO3. You can do that. What is the value of IPSO for this one? What is the value for this? From the table take it. Simply keep adding everything, and this is the value you are going to get. Okay. So, for all the carbons we have calculated, and then if you see this value what you calculated, of course this is 148.3 the value calculated. Experimental is given as 148.23. Look at this one. This is the calculated value. Experiment is very close by. There is not much. Look at this one, 131.4 is calculated. Experimental is 131.5. So, very easily you can start making the assignments. This is how you can use this value, but there could be deviations. I am not telling these are the accurate values, but they come close to the experimental value. You can use this as a starting parameter. Your assignment will be fairly accurate. Plus, you have to use the chemical shift ideas, and then in case if wherever you require, you can use other techniques. So, this is the way we can start interpreting the spectrum. Okay, we know how to analyze the spectrum. We know how to record the spectrum, how to interpret the carbon 13 spectrum, especially the phenyl carbons based on the substituent. Of course, there are several other tables for several other types of groups. Using the steric effect, we can calculate the chemical shift for linear chain molecules. There are aliphatic groups for CH3 chemical shift, CH2, CH3 in a long chain also we can do. There are several tables for that. Using steric effect, for example, particular carbon, how many bonds away it has CH2, CH3, how many carbons are there, how many CH2s are there, how many CHs are there. Each of them you can calculate, use the value, and then get the additive value for a particular carbon and predict the chemical shift. It is possible for that also by using steric effects. I am not going into the details of that, but just I wanted to tell you that itself will take enormous amount of time if you want to discuss. In most of the books, this steric effect and the values are given, like the table which I showed you is given in books. Simply take that, start using it for the analysis. Next, we want to understand the coupling between the carbon and other spins. Carbon 13 can also couple other spins, like we saw in the proton case, proton phosphorus, proton fluorine, proton carbon coupling we got. Carbon 13 can also couple. See, carbon 13 coupling, usually we record the spectrum in deuterium. What happens when carbon coupled to deuterium? How many peaks we expect? Remember, carbon 13 is spin half, this is spin 1. So, obviously, we get 3 lanes of equal intensity, and usually these solvent peaks are not protonated. As a consequence, they will not relax faster, they are weak in intensity. Take for example CdCl3, this is a solvent normally used for organic molecules, and it comes at 77, you get 3 peaks of equal intensity. This separation gives you coupling between carbon and deuterium. Very simple. If you go to this CD3CO CD3, CO carbon has no deuterium attached, gives a single peak. CD3, when 3 deuteriums are attached to a particular carbon, you can calculate the intensity pattern also. It is going to give you, see, 7 line pattern, 1, 2, 3, 4, 5, 6, 7. Septet pattern you are going to get with different intensities which can be worked out. For when you have a dimethyl CD3CO CD3, This is the pattern you get. When you have a dimethyl sulfoxide like this, again 7 line pattern because there are 3 CD3s are present. CD3OD, we get pattern like that, again 7. C6D6, similar to CDCl3, we get 3 line pattern because all carbons are equivalent and all deuteriums are equivalent, you get 3 peaks of equal intensity. CD2Cl2, there are 2 deuteriums are present, you get only 5 lines, unless 3 deuterium you get 7 lines, here you get 5 lines of intensity different. We also worked out once, there are 2 deuterium coupled. Remember when I was working out CH2D2 molecule in the proton spectrum, when we simulated, we also worked out the intensity pattern. It is 1, 2, 3 to 1 intensity we got, exactly 5 peak. Similarly, because proton and carbon both are spin half, when it is coupled to 2 deuterium, the intensity pattern remains same. Pyridine D5, pyridine has 3 different types of carbons, orthocarbon, metacarbon and ipsocarbon, all will give rise to intensities, triplet, or if we don't say triplet, triplet in NMR jargon is 1:2:1, I would say it is a 3 lines of equal intensity. And especially ipsocarbon, as I told you, the relaxation is slow, not attached to proton also, will get a lower intensity. And when you want to record the spectrum, you can measure the coupling. Let us look at the carbon 13 spectrum of this molecule. If there is this carbon, I am looking at the carbon fluorine coupling. Carbon can also couple to proton, that we can extract easily. When it is coupled to fluorine and also proton, both abundant spins are there, you will complicate the spectrum. Spectrum gets terribly complicated. How do you simplify that? I told you already in the proton analysis, I told you at the end, we can break the coupling of one of them to simplify the spectrum. Do this. You break the coupling with proton, all protons coupled, all carbons are removed. But I told you other nuclei are still coupled, so fluorine is still coupled. You are breaking coupling with carbon proton, but fluorine carbon coupling is still present. So then how many different carbons are there? One is CH3, 1, 2, 3. There are 3 different carbons, you have 3 different spectra. So only 3 different peaks. This is CH3 peak, this is CH3F, this is CO. And you see this is the fluorine, this fluorine is directly attached to this carbon. Of course, this is also there, this is 1 bond coupling is there, this CH2F, and this CO has 2 bond coupling, this is 3 bond coupling, 1, 2, 3 bond coupling, this is CH3. This carbon of CH3 can couple to this fluorine, but very weak coupling, 3 bond coupling far away. Largest coupling is 1 bond, this carbon to this fluorine, 185 Hertz, and this is 20 Hertz. Mind you, 1 bond CF couplings are always negative, but it is not written here, but it is negative. You can interpret that. Another molecule, it is very simple. This is carbon 13 spectrum in CDCl3. How many peaks you are going to get for this? How many carbons are there chemically inequivalent? Look at it, 1, 2 and 3. There are 3 different carbons. We will start interpreting this now. First I would say this is this carbon. You know why? This is a large quartet. Large quartet of this comes because of carbon coupled to 3 equivalent fluorines, CF3. CF3 carbon you see coming in this range and in the aromatic range. Usually we get aromatic protons, aromatic carbons here around 120, 130, but CF3 carbon is coming. Do not get surprised, all these things can happen in NMR. And you measure the separation, this is 280 Hertz. 1 bond CF coupling is very large. So I would fairly put this as 1JCF, and that is corresponding to this carbon. Go to the next one, 2JCF. Which is 2JCF? This carbon can couple to this. This is 32 Hertz, quite large, and that also has to be a quartet because same 3 equivalent fluorines are coupled. So you can see 3 equivalent this thing, and then 3J, this carbon can also couple to this, and it is going to be a quartet. So very easily you can understand all those things. Okay, this is the spectrum, a simple molecule where we are looking at only carbon fluorine couplings. Of course, proton couplings we are not seeing. And what is this peak? At 78, what is coming? The 3 peaks of equal intensity, because it is recorded in CDCl3. Carbon is coupled to deuterium and giving rise to 3 peaks of equal intensity. This is a solvent peak. So, like this you can start interpreting. Go to this molecule. This is a fairly simple molecule, 2-fluoropyridine, and there are different carbons. Of course, 2 and 6 are chemically equivalent, 3 and 5 are equivalent. So, only there are 4 different carbons present. I am sorry, 3 different carbons present here. Oh, I am sorry, there is no symmetry because this fluorine is here. All 5 carbons are different. There is no symmetry because this is not proton, this is a fluorine. So, pyridine has symmetry, but 2-fluoropyridine has no symmetry. So, all carbons, 5 carbons are chemically inequivalent. What is the largest coupling we can think of? Largest coupling we can think of is one bond, this one. Look at this, it is a doublet. Again proton decoupling, you will get only carbon fluorine couplings. Second largest is what? Look at it, 2 bond coupling. Which is the 2 bond coupling? This carbon to this fluorine, quite large. I can assign this as carbon 3 and I can assign this as carbon 2. The numbering starts from 1 as nitrogen. So, this is carbon 2, this is carbon 3. What is the next one? Next is 3 bond coupling. There are 2 3 bond couplings, this one and this one, C4 and C6, and one of them is, this is quite large compared to this. Both that can be interpreted. And the last one is this one, this carbon. This carbon has a 4 bond coupling, very weak, and these values have been measured. You can see it, 1 bond coupling, 2 bond, 3 bond coupling, 4 and 5 bond couplings. As the number of consecutive bonds increases, interestingly here couplings are coming down. Systematically they are coming down. 1 bond is larger, then 2 bond, then 3 bond, then 4 bond. We look for carbon 13 spectrum of a simple molecule, not simple molecule, a mixture of molecules, not one molecule, 3 molecules. That is CH2Cl2 dichloromethane, CHDCl2, CD2Cl2 and CH2Cl2. See, this is 3 molecules are present. Of course, CH2Cl2 spectrum we will consider first. 3 molecules are CH2Cl2, CHDCl2, CD2Cl2. When I look for CH2Cl2, how many peaks we expect? I am not decoupling. It is proton coupled. See here, simply written 13C. If it is decoupled, I would have written in flower bracket 1H. That means proton is decoupled. Here that is not written. It means carbon is coupled to proton. When this carbon is coupled to proton, how many peaks we expect for carbon 13 of CH2Cl2? Already I told you there are 2 equivalent protons, it has to be a triplet. Can you see a triplet pattern here? Obviously, this large triplet gives you 1 bond CH coupling, this corresponds to 1 bond CH, that is CH2Cl2 triplet. Very clear. There is no confusion about it. I can put it as this one. Then go further. This gives me 1 bond coupling. Go further. I will take other molecule now. Other molecule is CHDCl2. What is the pattern we expect for CHDCl2? You should remember this carbon splits into a doublet because of proton coupling, and each lane of this doublet will be 3 lanes because of deuterium coupling. And where do you get that pattern? If you look at the spectrum, you can identify that pattern like this, identical, but it is not exactly at the center of CHCl3. See, it has moved a bit, chemical shift has moved a bit. This is because of isotopic substitution. This is called isotopic effect. Because one proton is replaced by deuterium, its chemical shift has moved a bit, because identical environment is not there. CH2Cl2 has one environment, CHDCl2 has different environment. As a consequence, its chemical shift has moved. But remember, substitution of a heavy atom always moves to the right. So, the chemical shift is coming to the right. Please remember, substitution of a heavy atom moves the peak to the right. This is what happened. And this is the chemical shift of CHDCl2. From the center of the chemical shift, there is a doublet, and each lane of the doublet is split into triplet, and this is the doublet that corresponds to 1JCH. and each line of that is split into this thing, three lines of equal intensity, that gives rise to JCD, coupling between carbon and deuterium. What is the last one you can think of? Last one is CD to Cl2. There are no protons here. Directly carbon is coupled to D2. I told you already, it gives rise to 1, 2, 3 to 1 intensity pattern, 5 line pattern, because of 2 equivalent deuterium splitting this carbon. And this is the pattern you are going to get, and this is what it is. And you see, this is the chemical shift. It has again moved this from this and also moved from this to the right. That is what I said. With the substitution of heavier isotope, chemical shifts always move towards the higher field. And this separation of any of these 5 peaks you take, adjacent peaks you take, that gives you JCD. So, very easily you can analyze this also. Okay. From this, J carbon deuterium coupling has been obtained as some value. So, there is isotope shift. Isotope shift, mind you, is always expressed in fact, lower value it will be expressed in ppb, but in this case quite large. ppm is per deuterium how much it is you can calculate. Okay, so we can start analyzing one molecule, and then before we go further, and then we can stop and then discuss many other things in carbon 13 later. This is a simple molecule. Carbon 13 proton broadband decoupled, which is very nicely written. I should have written here 1H in the flower bracket. What is the type of spectrum you are going to get for this molecule? Very simple. First it is TMS, that is a reference, TMS carbon, and of course what are these 3 peaks which are coming? Equal intensity, CdCl3 solvent, and this correspond to coupling between carbon and deuterium, that comes at 78 ppm approximately. That is also fine. Now we have to understand these peaks. What are these peaks? Why are they coming? If you see carefully, this is a large quartet. You can measure the separation of this quartet. That is a huge value, large separation, and value is about 284 hertz. Where it can be? It can be from which carbon? Obviously it is from CF3 carbon. CF3 directly attached carbon fluorine. These 3 fluorines will split this into a quartet. This is a CF3 group. But simultaneously, this carbon is also coupled to this fluorine. You understand? Simultaneously, COOH carbon is also coupled to fluorine. Again 3 fluorines chemically equivalent, split this carbon also into quartet, 2 bond coupling. This is a 2 bond carbon fluorine coupling, this is a 1 bond carbon fluorine coupling. And 1 bond carbon fluorine coupling is about 284 hertz and 2 bond is about 44 hertz. Very easily you can interpret the spectrum. Here you are directly detecting carbon. Question of satellite does not arise. Remember, you are directly detecting carbon. So, fluorine is abundant. When you are detecting the low dilute spin, as good as you are seeing the abundant spin. So, when they couple to abundant spin, you will get splittings like this. Very easily you can extract heteronuclear couplings in these molecules. I hope you got the point now. So, now since the time is getting up, what I am going to do is, I will stop here. What we did in this class, we started with we started understanding how to interpret the carbon 13 spectrum, simple spectrum. I said intensity of the peaks depends upon chemical equivalence, how many carbons are chemically equivalent. If there are 2 equivalent, then intensity will be doubled. And also I said quaternary carbons, ipso carbons which are not protonated, usually will have very low intensity because they relaxes very slowly. And I said you have to give 5 times the longest T1 of the particular carbon as a relaxation delay, so that all the carbons will be of equal intensity. That is one thing. And also I showed you how to make the assignment of different carbons based on the multiplicity pattern or on the chemical shift. Multiplicity pattern was not there because we decoupled proton, only based on the chemical shift. But how do you know which is the chemical shift? Especially for the phenyl groups, we have a substituent effect, like we did for the protons. For different substituents in a phenyl group, have a contribution to our different sites, ortho, meta and para positions, and there is a table available for that. Use these values, start the basic value of benzene, whatever the basic value which I showed for benzene, 124 for something, that you take that value, co-add with all these other additive values of the substituents, you get the approximate value of carbon chemical shifts for different carbons. And then use this as a starting point to get the experimental value, precise experimental values will be known, you can make the assignment. Then I also said protons can couple to abundant species, carbon can couple to abundant species like phosphorus, fluorine, etc. And we took the example of the carbon fluorine coupling and how the spectrum gets complexed. Of course, we remove the decoupling of do the decoupling and remove proton couplings, but still heteronuclei like fluorine, phosphorus, others, if they are present, they are coupled. So how do you analyze that? And we took the example of 1 or 2 molecules and we measure the carbon fluorine couplings and we saw how this multiplicity comes with 1 bond coupling, 2 bond coupling. We can have the carbon coupling up to 3 bond, 4 bond, we saw in the example of 2-fluoropyridine up to 4 bond coupling. So in some other molecule also we saw up to 3 bond and 4 bond coupling. So a couple of examples we took to understand, analyze and extract the heteronuclear coupling between carbon and fluorine. With this I am going to stop here. We will continue for the next class where I will give you some other information, some more things about how you can use carbon 13 to get the structural information. Thank you very much.